Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 8, 2025, just a few days ago. The really interesting finding here is that memory built by a powerful model like GPT-4o can be transferred to a weaker one, boosting its task completion by 5%. The paper is titled Memp, Exploring Agent Procedural Memory, and it introduces a really clever way for AI agents to learn from their mistakes. This paper introduces a framework that lets agents build, retrieve, and continuously update a kind of how-to memory from past experiences, making them more efficient and successful at new, similar tasks. And this first figure illustrates the core idea perfectly. In the top scenario, we see the problem. An agent gets a task, but with no memory, it's just guessing. The process is full of trial and error, making it slow and often inaccurate. But then, the bottom scenario shows the solution. The agent is now equipped with procedural memory. When it gets a similar task, it can look up how it succeeded before, allowing it to follow a correct path from the start, making it much faster and more accurate. So this diagram really lays out the framework's three key stages. First up is the build phase, where the system distills past tasks and their outcomes into a structured procedural memory. Then, in the retrieve stage, when a new similar task appears, a retriever finds the most relevant memory to guide the agent, and this all feeds into the update cycle, where new experiences are used to refine the memory storage. This cycle adds successful paths, corrects errors, and even deletes memories from failed attempts, constantly improving performance over time. This table then details the results for different retrieval policies on the travel planner benchmark. The authors tested several approaches, having no memory, randomly sampling a memory, and two smarter methods. One is a query-based method, which finds memories using the whole task description, and the other, Avenue Fact, focuses on matching keywords from the task. And the results are clear. For every model, from GPT-4o to QWin 2.572b, the intelligent retrieval methods like Avenue Fact consistently lead to higher success rates and fewer steps to solve the task compared to the baselines. Building on that, this table looks at how the memory is constructed in the first place, or the build policy. We see results for four approaches: using no memory, storing raw trajectories, creating high-level scripts, and proceduralization, which combines the two. Across all models, like GPT-4o, the proceduralization method is the clear winner. It delivers the highest success rates and the lowest number of steps, showing that a mix of abstract rules and concrete examples is the most effective way to build this procedural memory. Alright, so after deciding how to build the memory, the next question is how to update it. These graphs compare three different update strategies over time. There's a basic vanilla update, a validation strategy that only stores successful attempts, and an adjustment method that actively corrects memories after a failure. The graph on the left tracks the reward improvement, while the one on the right shows the reduction in steps. The trend is clear. The adjustment strategy, shown in green, consistently outperforms the others, leading to the highest scores and greatest efficiency. So, to wrap up, this work makes it clear that a dynamic, self-correcting memory is crucial for agent success. Combining abstract rules with concrete examples and actively learning from failures makes these agents far more efficient and capable. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.